So in this video, we're going to look at pendulum. This is yet another example of harmonic motion, and I want to contrast what we see here with a spring on a mass. So our pendulum, here's the string. It's hanging from some fixed point up here, and let's draw a circular mass on the end. That mass is mass m. We'll say that the string has a length of L, and it departs from the vertical by some angle of theta. Alright, now, in order to solve a problem like this easily, we need to do a torque calculation. It could be done, I imagine, with forces, but torque is generally the easiest way to proceed here. So, the forces in question, really there's one force that's doing the work here. It's gravity. So, this particular force is mg. Well, the torque it exerts here goes at a right angle to the direction of the wire. So that right angle direction, let's see, if that angle is theta, this angle over here is also theta, and we end up having an mg sine theta being the force, the component of the force that contributes towards the torque. The component that goes along the wire, of course, doesn't do anything except pulls on the wire and adds to the tension. So, if we do an analysis like this, it looks something like what follows. The sum of the torques is equal to the moment of inertia times the angular velocity, and that, in turn, is equal to, well, I'm going to write a negative here, negative mg sine theta, and that's in what direction? That's in the positive theta direction, so basically it's rotating like that. So, why the negative sign? Well, the negative sign is indicative of what we call a restoring torque. So we could sort of get into some semantics about sign here, but I want to sort of follow through and really focus on how this particular equation is similar to what we had before. So when we talked about forces and our spring mass system, we had something very similar. Ma equals negative kx, and here that negative sign really should be associated with the x hat vector. What I want to draw your attention to is the analogy between some of these things. For example, moment of inertia is the rotational analog of mass. Angular acceleration is the rotational analog of linear acceleration. Theta, well, we're going to get to this. Theta is the rotational analog of position x. Now, we have a sine theta, not a theta. Well, I would invite you to, using radians, enter into your calculator some angle, some very small angle. Take something, say, 7 degrees or less, and enter that theta in, and then do a calculation of sine theta. And you will see that, in fact, in your calculator, theta is approximately sine theta for very small angles, if we speak in radians. So this first equation right here is actually going to turn into the following. We will cancel out our vectors, and we'll have the moment of inertia times alpha is equal to negative mg theta. It's really an approximation, but for all intents and purposes, as long as you have small oscillations, it works really well. Now, let's beat this into shape a little bit. We have I alpha plus mg theta is equal to 0. Now, if you recall, the moment of inertia, I, can be written as the sum of all mass points in an object times their individual radii squared from the point of rotation. So here's the point of the rotation. We have a mass m at some length L. The moment of inertia in this case is very simple. It's simply ml squared. So we can write m L squared times alpha plus mg times theta is equal to 0. Furthermore, let's get a new page up, and I'll have to scroll up a little bit. Furthermore, if we do a little bit of division here, oh, what did we leave out? Oh my goodness, we left out something very important here. In our torque, we have a force. See, this is a torque, this is actually a force. We left something very critical out. There's an L there. There is an L here, and there is an L here, and an L there. So, right, so if I get a chance, I'll redo this with that in place so nobody's confused, but really there needs to be an L in place there. Now, I caught that because I was looking at this and I saw something that did not cancel properly. So now we'll do a little division. We'll divide everything by ml squared, and that'll leave us with alpha plus, well, look what happens. 1 power of L is going to cancel, and the masses are going to cancel. And what we're going to be left with, there's the power of L in the numerator, we're going to be left with alpha plus g over L times theta is equal to 0. Now compare that to what we had for the spring mass system. That looked like the acceleration plus k over m times x is equal to 0. Mathematically, these are related exactly the same way. Alpha and theta have the same relationship between each other as a and x. So keeping that in mind, whereas in the spring mass system we had something like omega squared is equal to k over m, in the pendulum system we have omega squared is equal to g over L. Now, in the spring mass system, I said if you were in space and you want to measure a mass, you put it on the end of a spring and you let it oscillate, and of course hopefully you know the spring constant k. You measure the period omega, or the angular frequency omega, by getting the period, and then you can go back and calculate the mass. So mass was equal to k over omega squared. Well, it turns out that pendulums don't work that way. They are dependent on the value of the local value of gravity where you are. So, for example, you could, if you knew the length of the pendulum to a very precise degree, you could, let's write it the other way, you could in fact get the acceleration of gravity via that equation. Notice the units, we have a length and we have an angular velocity squared, so that all pans out. It works very nicely. So you have to know this within a very fine degree and make sure that your string doesn't stretch or anything else, but that's one experiment that you can do to determine the value of gravity. If, for example, you don't have a ruler and you presume that gravity is 9.8 or 9.81 or 9.79, if you know the value of gravity in your area and you want to measure the length of the string, well, you can do the other way. You can write L is equal to g over omega squared. So you've got your stopwatch on your iPhone or whatever it is you have. If you're like me, you're a runner and you have a regular stopwatch, you know the value of gravity and you can solve for L. You can actually make length measurements. So there's the analog. So pendular motion, oscillatory motion due to springs and masses, and in fact circular motion all have some things in common.